So let's click.
So you're in charge now?
You guys been studying? Yes? Yeah, if you don't, you're not saying yes, you're already behind, right? So remember, this is going to be pretty quick.
I'm saying yes.
Quiet, please. All right, guys, let's go. Come on, man. It's not high school. Let's move. So, it moves fast, yeah? So you need to be on top of your game. So don't wait. Now's the time. You wait past this week, there's not going to be enough time to catch up for the midterm, all right? We'll cover a lot of material this week. So it's really important. How the computation sets go. So there was a fill-in from my TA, right? Dr. Adam Lambert. Everything went fine, smooth? Great. So that's kind of the basic framework of it. I highly recommend you attending those and doing it because that's an easy 20% of your examination. Boom, stuff like that, right? They take time. They're not difficult to do, but just knowing what equations to use, when to apply them, and how to run through it is important. As we make our way through the ecology portion of the class, the equations that you use will get more complex. And so basically they'll start to add upon each other. The math is just simple. But learning how to use the equation and when to apply it properly is really important. And just because there's more orders of operation on a longer equation set, it's easier to make a simple mistake when you're under pressure. And so you don't want to do that and lose points because of that. So I highly advise doing it. It's a head start on the examination. You know they're coming, there's no surprise, and you're well set up for the rest of the exam, right? Worst thing that can happen to you is come in, not practice it, get hit with a computation, not know it, get stressed, and then everything behind that is more difficult, right? You always want to set yourself up for positive returns, not negative returns. Now remember, it's nice and cool and comfortable here today, but I have no idea what it's going to be another couple Thursdays from now, right? So who knows, it might break down, it might not be turned on that day, and so you never know what the testing environment's going to be. So add your stress of taking an examination on top of heat, that's tough too, right? And then you guys are charging over here from another room across campus, yeah? So that adds to it too. Make sure you get out early that day, so that you're not freaking out running from room to room as we're starting to hand out exams as well. Any questions before we get started? Okay. Well, let's do some review. We were finishing up talking about the distribution of organisms. And so let's review that material. I can't remember the first slide I talked about that day. Was it competition? Is that it? Let's start with competition. Definitions. Yes? All right, let's do that again. So competition by definition, what is it? Negative, positive, 0 plus, negative. How do you measure that? At the population growth rate level. So when you're both into that particular interaction, then it's negative for both of you. You have less offspring. You have to sacrifice energy. All right, so let's kind of walk through the basic ideas of how you would code for competition. Competition within a species, what's that? Interest between two different species. Very good. What if I physically touch you in the interaction? Interfering. What if I'm just quicker at getting it and I mediate it through the resource? Exploitative. How do you code it first? If I wanted to say it and I wanted to tell me what kind of competition it was, first I'd look at what? The species interaction or the form of it in terms of direct or non-direct? I look at it's in or between species first, and then I go and I see what the form of it is, right? That's how you do it. On an examination, don't make that error. Look carefully. It says competition, and one says intraspecific competition. An intraspecific competition is a better answer. That's the answer, not competition. Okay, so make sure you read the questions carefully and look at those answers tightly, all right? I've had lots of people come into my office hours and ask about the nature of questions. I'll post some, I've already posted some study questions, go take a look at them. But it's going to be example-based. I'm not going to say, again, what is the definition of population? 2 or more species, 2 or more individuals, same species defined. You're not going to see that. What you're going to see is an example. 5 woodpeckers are on oak trees pecking, blah, 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 in this particular hectare of forest. What's that? Well, that's what you'd see as an ecologist. You go out, you make an observation, and then you fit it to what you know. And that's what the exam will look like. Think about the computations. That's exactly what they do. Here would be a question. Do you reject or accept the null? Well, I don't know unless I actually do the computation to give me the answer, right? And it's going to spit out a value that's interpreted, telling you how that answer is. That's what your exam is going to look like. So it's either going to be mathematical computations or it's going to be, mental problems to be solved like that, making the two-step process of what you've learned and then applying. Okay? Some stuff's easy. Who did this and why do you know? Verhulst, what they do? What did Verhulst come up with? The logistic equation, right? So in that, am I going to give you an example of that? No. Professor such and such was sitting in, no, of course not, right? So that's just something verbatim. So remember, the first step is always learn the information, and then the second step is apply. But some things are just at that base level. And a certain portion of the exam is always kind of at that base level. So be prepared for both styles. If two species are found tightly knotted up to each other but not overlapping, what might that indicate to you? Strong competition. If I take one away and the other operates and takes over the new area, what would that be called? That would be competitive release. Very good. All right. So we talked a lot about some classical studies in ecology, one of those being the work of Joseph Connell, right? In this particular one, we're interested in using our primary tool for learning about distribution, that's the transplant experiment. What barnacle is found at the top? Thamlis, the big or small? That's a small one. Which one's found in the middle? Balanus, which is the big one. What's found below that? Thias, which is the predatory snail. What controls the lower limit of the small barnacle Thamlis? Be specific. Interspecific competition. What is it? Interspecific interference competition. Why was it interference? Because it popped them off the rocks, right? What sets the upper limit of the big barnacle Balanus? An abiotic factor, which is desiccation. Very good. What sets the lower limit of the big barnacle Balanus? The lower limit of the big barnacle. A biotic factor, which is predation. Very good. What sets the upper limit of the predatory snail? Thias. An abiotic factor, which is desiccation. There you go. Okay, so that was a nice experiment which showed lots of interplay in the biotic and abiotic factors of an environment, setting the distribution patterns of organisms. We talked about what's the difference between adaptation and acclimation? Acclimation is short or long term? Short term. Physiological, morphological behavior, short term events. Adaptation, on the other hand, is what? Long-term evolutionary change, right? Modifications in your genetic structure. All right, so what's typically the lower lethal limit for most organisms? 0. Why? Cells burst because you go from liquid to solid and you rupture the cell membrane. What's the upper limit for most? 45. Why? In denatured proteins are no longer functional. Can you exceed those thermal barriers? Yeah, lots of organisms do. But the majority are found between those boundaries. But there's definitely exceptions. Water loss is a big issue, right? So water balance is really critically important for your metabolism and basically maintaining the qualities of life. So if you're a saltwater fish, what's your problem? You're going to do what? Your cells they'll shrink. How do you deal with it? You drink. That's an easy one. If you're a freshwater fish, your cells will do what? They'll expand and explode unless you pee, which is what they do to pee out the water. And for you lose water constantly through a variety of mechanisms. How do you deal with it? You drink or you eat. Okay, there's a lot of water and food. There are certain organisms that are really well adapted for dry climates. Things like kangaroo rat. Certain kangaroo rats only have to take one drink a year. They get all their moisture from the food. That's how efficient they are. Okay? Because there's always water, that content that's found in food. We talked a lot about light. Light quality and intensity is really important because it's going to drive primary producers. Primary producer distribution will determine what? Animal distribution. Okay? So the plants dictate where we can live, is basically what it comes down to. We talked about soil structure and soil composition. And so I gave you an experiment dealing with serpentine soil. What are their characteristics? They're high in what? Nickel and magnesium. So they have a lot of these heavy metals in them. So therefore we might think that they're what? Benign? The benign soils, if that's the case? No, they're full of lots of nasty stuff. So we might think they're toxic. So we look out there, what's our observation? Normal plants grow great in the sandstone soils around the serpentine, but do they grow on the serpentine?
No.
They do not. What flower grows on the serpentine? The goldfield flower does, but it does not grow outside. What's your question? Why? What's your tool to test it? It's a transplant experiment. So what do? You take the flowers on the sandstone soil, and you transplant them on the serpentine soil, and they die. Can you say with confidence that they are the soil toxicity led to their elimination?
No.
No, why not?
No control.
No control. Very good. What would be my control?
Moving next.
I dig up the sandstone soil plants and do what with them? I put them right back in. What's that telling me? Do they survive if I do that? Yes. And that tells me that the transplant itself is okay. Because transplant is pretty stressful. Sometimes you grab a plant from a nursery or something like that, throw it in the ground, and it just heals right over. That's a pretty traumatic thing. These are living organisms, right? That's a pretty stressful event. But in this case, they control it well, it's replicated well. And so you move them into the serpentine soil, what happens to the normal plants? They all die. So what's the limitation to distribution? An abiotic factor, which is soil toxicity. Too many heavy metals. Now what's the primary reason that they can't survive? Because the soil's doing what? Binding calcium, which the plants need. All right, and that's the problem. They can't acquiesce to the calcium, and therefore they die. They can't drive the metabolism. All right, let's do the opposite transplant. Move the goldfields out. There's a problem here, however. It's easy to move the sandstone flowers onto the serpentine soil because often there's nothing growing there except it's blank, yes? But if I move goldfield flowers out onto the sandstone, what's the problem? There's tons of other organisms out there. I can't find any blank space, so I have to create it. So I need to transplant them with and without what? Without those flowers, which are their competitors. If I move the goldfield flowers outside onto the sandstone soil without the competitors, do they grow and exist?
Yes.
Do they reproduce?
Yes.
Yeah, they do great. So what does that tell you? Is it soil toxicity out there?
No.
Is there anything wrong with the abiotic environment?
No.
They do fine. However, when I transplant them with their competitors, now what happens? They all die. So what does that tell you? Goldfield flower distribution is limited by what? Biotic factor, which is it is interspecific and the form. I didn't tell you. You know what it is? It's actually both. They both do it in direct interactions by touching and overtopping, and indirect interactions by grabbing sunlight, nutrients, and things like that. All right. So it is an interspecific form of competition, both exploitation and interference. Okay, good. Is that where we stop? Or do we go further? That's where we stop. All right, well, that's a good place. All right, so disturbance. You might think disturbance is a bad thing. You flip something over, it fills a bunch of stuff, a storm comes in, rips everything up. So it really depends on your viewpoint. So periodic disturbance is not necessarily a bad thing. It depends on its frequency and its intensity. So basically, when you get catastrophic disturbances like these massive fires that we've had that burn extremely hot, thousands of hectares, that's a pretty dramatic event. These massive hurricanes that we've been getting worked with, both of those things are direct outcomes of the shift in the climate. Are there more hurricanes now than there were in the past? No, there aren't. That's an interesting misnomer. However, they're more what? They're way more powerful. So we get much more powerful hurricanes that are occurring with the rate. Lots of, what we get last year, like 3, 5 right in a row? 3 back-to-back 5s or something like that? I mean, it's pretty amazing. You never see that normally, right? But that's how it happens. So you can have frequent disturbance. Now, you might think that frequent disturbance is a bad thing. But it's not really. Because anything that is, I can't speak, I had a word, it just stuck there, predictable. If you have something that's frequent but predictable, is that such a bad thing biologically? No. Frequent and predictable means you can do what? Adapt to it. That's exactly right. But infrequent and intense, you can't adapt to that because it's unpredictable in nature when it's going to occur. Even intensity can be dealt with as long as it's predictable. But in this case, unpredictability, infrequent, no. That's when you get blasted and you can lose everything. So infrequent disturbance is unpredictable, and that can really have dramatic impacts on both abundance and distribution. Whereas frequent disturbance of relative moderate magnitude can actually be quite easy to adapt to, and you will see lots of strict distributional changes based around that. So let's take a look then at a classic example right here in our local chaparral. So get out of class, look up at the hills, and that's the kind of habitat we're in, local chaparral. Well, it burns. And it's been burning every year. It shouldn't burn every year, but it has been burning almost every year. And last year was brutal, right? So I live in Ventura. Ventura burned everywhere. It was terrible. A bunch of my friends lost their house. The hillsides were devastated. Hundreds of homes had swung all the way over here. It burnt stuff over here. Luckily, it didn't sweep down into Gleed or anything like that very badly. We just had a local Gleed fire too, right? So this is ongoing. They're really intense. And so what happens basically is the chaparral burns. Now I'm going to talk about a normal burning pattern of how it used to be. And that is the chaparral would build up over time. You have a fire. It looks like it's a pretty heavy consequence of that. It looks pretty bad. But then lo and behold, the very next year it looks like this. And you have all these annual flowers, tons of different types of vegetation. Species diversity is extremely high. That's the normal course of events. And many communities are really well adapted to that. So for instance, this type of normal fire cycle is very easy to adapt to because it's frequent and it's regular and predictable. So when is it going to burn in a typical year here in California? In summertime, right? It's going to burn typically sometime from June, not even June most of the time, like July through September. And then it's going to rain in October sometime, and your rainy season starts and there's no more fires. That's the way it used to be. That is no longer the case. Fire season is now all year long. Okay? So that stopped several years ago, and this is what we're left with. But it used to be that that's when it would burn. Burn a couple months in the summer, the rest of the time it's not burning. And when you actually did a survey of those burns, what you saw is that a typical plot of land in chaparral burns every 14 to 25 years. So you get a fire, 14 to 25 years later, you're likely to get a fire in the same spot. How are natural fires most of the time started? Lightning is the #1 cause. There's a lightning strike every second on Earth, okay? So lightning strikes are the most common way. That's no longer the case in urbanized areas. What's the most common way to start fires? Human stupidity. All right? So that's how we do it. It's machinery sparking, idiots throwing cigarettes out the windows, people with campfires, whatever it might be. That's how most of them get started in urbanized areas right now. And so we have a problem because this fire cycle is no longer how it used to be. So we have kind of this cyclic cycle, right? Chaparral burns. You get when you get chaparral burn and all that ash that gets laid down. What is ash? You decouple ash down to its component forms. What is it?
Carbon.
It's carbon. It's nitrogen and it's phosphorus. So therefore, it's what? It's fertilizer. It's the stuff you spread on your lawn to make it look pretty, right? So you hit that with a little bit of water, and that's why you get that. Not only that, but you reduce all the competition because chaparral was squeezing everything out, and then you get all these nice annual plants that come to the top. All right. So what's going on with this here locally? Well, what's happened is because the climate has shifted and we've built so much in the foothills, the first thing we've done is suppress fires. So the natural burn cycle is 14 to 25 years. But where do all the people who have money like to live? They live on the hills or they live?
By the water.
In the water, and then everybody else is in the hill. Okay? That's kind of how it works. And so especially if you're in Santa Barbara, if I have a little falling down shack and it's in the hills or on the beach, how much is it worth? Like $2 million minimum, right? That's minimum. Most of them are in double-digit millions, okay? So, therefore, if I have a fire, I don't want it to burn down. So there's heavy suppression of fire that goes on when it probably shouldn't. So what happens is even burns that are in kind of places that there's nothing around are instantly put out. That's bad because what happens is fuel burns up over time. So instead of burning over 14 to 25, maybe it's been 100 years since the last burn. And so what happens is that chaparral gets bigger, thicker, denser, packed together, accumulates volatile organic oils that then sit there, and when fire hits it, it goes up like a bomb, right? And it burns way hotter than it normally would burn. It burns so hot that it actually damages the apparatus that these plants have for being adapted to fires. A normal 14 to 25-year-old fire would burn off the top, lay down the ash. All the root systems are still completely intact as they're adapted for surface fires. Within a matter of days, they're resprouted. But if you burn them that hot, that will basically bake the internal structures. There's enough heat penetration of the soil that kills it. Then the second thing happens. Once you do get a fire, the homeowners below the fire zones know what's happening when it rains. What's going to happen since you clear off everything? You're going to get mudslides because the soil's been destabilized. So they want that soil stabilized. So one way to stabilize it is, you ever seen the stuff that they put on after fires? It's kind of like lime green. Sometimes it's blue, and they lay it down on the hillsides.
Yeah.
Well, what that is basically a cellular-based composite that is made to stabilize the soil, hold it in place to allow the native vegetation to grow back quicker because the soil's not sliding around if it rains. And it's a pretty decent idea, and it does work, okay? However, the quality of that material varies quite a bit, all right? And like any business, people do a good job of it, and people do a poor job of it. So it's supposed to be a cellulose composite, meaning it's a lot of times it's like cardboard and things like that, but it's supposed to be a combination of like plant material and other things. But unfortunately, the cheaper you go with the product, the worse it gets. And so Santa Barbara in 2005 burned pretty extensively, all across the landscape, right? Hills were on fire everywhere, from like, you know, all the way down from Rincon, all the way up to Gaviota, we were on fire. And so the hillsides were barren, and people were scared about the mudslides. So they put this out to high as bitter, or to low as bitter, excuse me. And so when it came back, they did the lowest bitter, they put that stuff on the hillside. Lo and behold, lowest bitter was not so good, because they were using high quality cellulose. They were not. To hold their junk together, they had actually used a significant quality of plastic trash and ground it up into small pieces to hold the stuff together. So basically, they spread over hundreds of hectares of land, plastic garbage. Is that such a great idea?
No.
That's not a good idea. All right, so you made trash dump out of our local landscape. The other problem was it continued to burn. A fast shortcut to basically getting ground stabilization is to get stuff growing quickly. So in a lot of this hydro-mulching stuff, it's called hydro-mulch, what they do with it is they pre-seed it with grass. So it comes, it's like, you ever seen they do this on natural lawns? You put down the seed, you top it with stuff, and it holds it in place and it grows real fast, right? So they were basically seeding the hillsides like that. And you spray this stuff out of helicopters and planes and all kinds of stuff like that. Well, again, it went out to bid. And so they went to lowest bidder, without really thinking too closely about, well, what kind of grass seed was in the mulch. So when they put it up on the hillsides, lo and behold, the grass that grew there was not native chaparral grass from California. You know where it came from? It came from Africa. And that grass grew very fast, and it did stabilize the soil. But the problem is the areas of the savanna in which they harvested that grass seed burns at a different rate than ours does. So our product cycle is 14 to 25 years. This came from savanna land, not chaparral, and it burns at 8 to 10 years. So now you have a grass adapted for burning at a much faster frequency. So what happens is, as soon as it starts to dry out in the chaparral, it dries out first and creates big giant tufts of dried grass. Well, when you get anybody throwing something, or you get somebody with a fire, or you get a lightning strike, guess what ignites first in the hillside? Native grass or Africanized grass? African grass, which burns as tinder. And then it sets off another forest fire, which naturally wouldn't start in the first place because everything else is still wet. So it burns and burns everything up, but what comes back first now, after the fire? The Africanized grass, because it's adapted for that fire cycle. So what happens is it starts to take over the entire landscape and exclude all the native vegetation. So the first thing they did was pile trash all across our local landscape. And then they introduced an invasive species which outcompeted everything else and sped up our fire cycle. So now it burns much more regularly. Is that brilliance? Pretty crazy. You want to see the grass I'm talking about? When you guys come into campus, if you come into campus on the 217, look on the sides of the road because this is an invasive species that does really well in disturbed habitats. And you'll see it as pampas grass. And so what it looks like is these big tufts of grass, and they'll be kind of greenish blue, and then it'll have these big florets that stand up that are pink during the flowering season. You know what I'm talking about? They're right on the road coming in, and especially if you take the loop off of like, what's that road there? Hollister, and then there's that little road that comes down on the side right here and does a loop, and then spins onto campus. There's all along that loop is pampas grass, and you can see that stuff growing right there. All that's invasive brought into that manner. Isn't that crazy? So that's completely screwed up our fire cycle. Naturally, it's a good thing. If you alter it, it can be a very bad thing. All right. pH and salinity. Well, for aquatic organisms, this is really important. pH is a tough thing to deal with. The vast majority of organisms